At the end of our last class video, we asked a very important question, namely, what is gained by adopting a group-theoretic point of view in the case of CMA structures and CMA sequences? Before answering this, we should consider what we can know by way of the automorphisms and isomorphisms depicted on the hidden structures diagram. We need to clearly understand what conclusions can be drawn from applying the structure-preserving and/or structure-transforming mappings on this diagram. Equally important, we need to know what conclusions cannot be drawn by an appeal to the properties of these mappings. 1. First, we will consider the types of conclusions we can make based on the hidden structures diagram. Given one of the Bessey structures, two-cycle, mirrored, AMP, DMP, mirrored piles, or couple piles, we know the ending structure type after the application of one or more of the automorphisms and/or isomorphisms featured in the hidden structures diagram. Given our knowledge from above regarding the ending structure type of our transformed Bessey structure, we can deduce the relative location of our c-quivalent pairs. For instance, consider the two-cycle, which consists of a perfect alternation of red and black cards, where our sequence begins with a red card. After a random application of appropriate automorphisms and/or isomorphisms that eventually result in another likely different two-cycle structure, we can conclude the following regarding the ending structure. Cards in position 1 and 5 will have the same color. Cards in positions 2 and 6 will have the same color. Cards in position 3 and 7 will have the same color. Cards in position 4 and 8 will have the same color. Of course, because of the color composition of the starting packet, we know that there are two pairs of red cards and two pairs of black cards. But our knowledge of the structure of the transformed packet ends there. Now consider the types of conclusions we cannot draw based on the properties of the automorphisms and isomorphisms in the hidden structures diagram. We cannot, of course, know the exact ordering of the cards in this two-cycle structure. We cannot know the precise locations of the pairs of red cards, or equivalently, the pairs of black cards. This is because there are many two cycles that can be formed from 4 red cards and 4 black cards. For example, RRBB, RRBB. That's a two-cycle relative to card colors being the same, as is this one, RBBR, RBBR, or BRRB, BRRB, etc. We cannot know which red cards are paired together, or black cards for that matter, let alone the exact ordering of the cards within each of these pairs. Indeed, we cannot even know for certain the color of the first card in the sequence. Nonetheless, knowing that the ending structure is a two-cycle, we can still produce surprising results, as we have seen repeatedly throughout this course. A common ending for a performance involving 4 red cards and 4 black cards would be to reveal c-quivalent pairs of cards on the table. The surprisal value for such an outcome, were it to occur by chance alone, is 3.54 bits. What we would know for certain is that each pair consists of cards of the same color. What we would not know is which specific pairs on the table consist of red cards and which consist of black cards. Before we move on to consider how group theory might increase our knowledge of the ending structure of the starting packet, please note that this card sequence is actually a CMA sequence of structure type SOO. Why is this significant? We can apply properties of the group V8 when it acts on the set of CMA sequences of order 8. A group-theoretic perspective. From our study of CMA sequences of order 8 and the group V8, we know that the orbit of this CMA sequence is this set. It consists of the sequence itself and its inversion. This means that we can apply any of the 8 shuffle permutations in V8 to the CMA sequence, and we will know for certain that the ending structure will be either this or its inversion. So it's either left fixed as a CMA sequence or its inversion results. Consider what additional information this gives us beyond that provided by the hidden structures diagram. We now know that the ending two-cycle structure of this alternating packet of red and black cards will be either this or this. What are some conclusions that we can now draw that we could not draw when applying the properties of the mappings in the hidden structures diagram? Perhaps the most readily useful one is the following. You can now separate the red cards from the black cards by alternately dealing the cards into 2 piles. The surprisal value for such an outcome, were it to occur by chance alone, is now 5.12 bits. Caveat: we still, however, cannot know for certain which pile consists of the 4 red cards and which pile consists of the 4 black cards. To be able to know this, we will need a stronger group-theoretic property, namely the stabilizer subgroup. 3. Also, from our study of CMA sequences of order 8 and the group V8, we know that the stabilizer subgroup of this CMA sequence is this set of permutations. It is important to remember that V8 is abelian, which means that RT is equal to TR, but only RT has been listed. Similarly, for CRT, there are 5 other orderings of the shuffle permutations T, C, and R that are equivalent to CRT. This means, for example, that we can apply the 3 shuffles TCR in any order, but in the same quantity, and still preserve the exact SOO structure. Such being the case, the packet of alternating red-black, beginning with red, will survive any equal number of applications of the 3 shuffles T, C, and R. Consequently, this provides additional information about the ending structure that will allow us to know which of the 2 dealt out piles of 4 cards each consist of red cards and which pile consists of black cards. The surprisal value for this new outcome, were it to occur by chance alone, is now 6.12 bits. Please note that we still cannot know the precise ordering of these cards within their respective piles. To know this, we will again need a stronger property / result regarding our group V8 than the stabilizer subgroup of the CMA sequence here can provide. 4. Finally, we can judiciously use properties of the elements in V8 to achieve maximal surprisal for any packet of 8 cards. Maximal surprisal occurs if we successfully return the packet of 8 cards to its original order after ostensibly mixing the cards thoroughly. One way to achieve this would be to employ one of our earlier demonstrations from a previous class video, in which we allowed the spectator to freely choose the ordering for applying the T, C, and R shuffles within 4 sets of shuffling sequences. You may recall that we created a table like the one below, where the spectator freely chose the ordering of the 3 shuffles within each of the 4 rounds. Question: why are we guaranteed that the packet will be returned to its original order? Answer: recall that not only is the group V8 abelian, but each of its generators, T, C, and R, has order 2. Consequently, after completing the 4th round above, we will have performed each of the shuffles T, C, and R an even number of times, that is, 4 times, which guarantees that our starting packet of alternating red-black with red starting at the beginning, or any packet of 8 cards for that matter, will be perfectly restored to its original order. The surprisal value for this outcome, were it to occur by chance alone, is 15.3 bits. It is important to understand that in this ideal outcome, we would know more about the ending structure of the starting packet than we could deduce from the hidden structures diagram, or from the orbit of the CMA sequence, or from the stabilizer of the CMA sequence. Indeed, we would have perfect knowledge of the structure and ordering of the ending packet, provided we had complete knowledge of the starting sequence. Summary. Here's a chart comparing the surprisal values involving the CMA sequence for what has been discussed in this class video. 1. Using information provided by the hidden structures diagram, we can achieve a surprisal value of 3.54 bits. Using the information provided by the orbit of the CMA sequence, we can achieve a surprisal value of 5.12 bits. Using the information provided by the stabilizer subgroup of the CMA sequence, we can achieve a surprisal value of 6.12 bits. And finally, using the information provided by the entire group V8, we can achieve a surprisal value of 15.3 bits. Here's a hierarchy of structure preservation of a CMA sequence. 1. Hidden structures diagram. It preserves the Bessey structures, 2-cycle, mirrored, AMP, DMP, mirrored piles, coupled piles. Will represent its surprisal by S of 1. 2. Orbit of the CMA sequence. This preserves the CMA structure types, SOO, OSO, OOS, etc., will represent its surprisal by S of 2. 3. The stabilizer subgroup of the CMA sequence. It preserves the exact form of the CMA sequence. For example, 1, 0, 1, 0, 1, 0, 1, 0 will represent its surprisal by S of 3. 4. Products of non-identity group elements equivalent to the identity. This preserves the exact ordering of the starting sequence. Consequently, all structure is preserved. Will represent its surprisal by S of 4. And so here is a string of inequalities showing the relationship between these 4 levels of surprisal values. So before we end this video, I thought we would step through an example that would illustrate the differences between these different levels of knowledge regarding the ending structure of this particular packet. So we're starting with an alternating red-black structure. Now, of course, that can be associated with the CMA sequence 1, 0, 1, 0, 1, 0, 1, 0, where 0 is associated with a card being black, and 1 is associated with a card being red. Okay, so right now it is a 2-cycle relative to card color. Okay, so let's begin by using the hidden structures diagram and the mappings there and see what kinds of things we can deduce when using those mappings. Okay, so I will kind of tell you where we are at each stage. Right now this is a 2-cycle. Well, what can we do with 2 cycles that will preserve its 2-cycle structure? Well, a Charlier shuffle is an automorphism, right? Now, I'm not going to use every single mapping on our hidden structures diagram. Our video will be 3 hours long if we try to do that. So here is an automorphism, namely a Charlier shuffle on a 2-cycle. We could now, if we chose to, we could convert this 2-cycle to a mirrored structure. That would be fine. That's using our hidden structures diagram. Since it's mirrored, we can do as many LR shuffles, stacking left on right or right on left as we like. We could do some up jogs. That would be fine. Stacking either order. We could do a couple of overcoats. Maybe we'll do 5. That's where you coat the same number of cards twice. Okay, very good. We could actually even do a ferro. If you remember what a ferro is, that's where you take the top half and the bottom half and you perfectly interlace them. That's a ferro shuffle. That actually preserves mirrored structures as well. And at this point, if we wanted to, we could take it back to a 2-cycle by doing a mange. Okay, and from there we could do an LR inverse, right? Okay, so this will now be an AMP, correct? So we can stack these in any order because these are adjacent mirrored pairs already. So now, whoops, excuse me, it's an AMP at this point. We could do a mange to make it a mirrored if we like, and then we could do a 50% coating. It's a 2-cycle now. Okay, so we're back to a 2-cycle structure, having used just a few of the mappings on the hidden structures diagram. Well, what do we know about this packet? Do I know for sure the top card is red? No, I don't. In fact, it isn't. Do I know the exact ordering of the cards based on the original order? No, I don't actually. What are some things? Do I even know that it's alternating red-black? No, I only know that it's a 2-cycle. There's many different 2-cycles, right? So for example, This is a two-cycle relative to card color. This is a perfectly legitimate two-cycle relative to card color. But it is not an alternating packet of red, black, black, red, or vice versa. Okay? But it is a two-cycle, right? Look, those cards, first and fifth, same color, second and sixth, same color, third and seventh, and so forth. This is a two-cycle, which is what we would get if we faithfully use the various automorphisms and isomorphisms on the hidden structures diagram. So what the hidden structures diagram gives us is it tells us a fair amount. It tells us that this is a two-cycle. Well, you can do some wonderful things just with that information. Now, one thing I can't do that I will be able to do with some of these others is I cannot separate the reds from the blacks and know for sure that I've succeeded. Because we could have had any two-cycle structure here. So I would not know, okay, how would I separate the reds into one pile of 4 and the blacks into one? You can't. You wouldn't. You would need something more powerful, which is what we've been talking about with group theory. Okay, but there's still some great things that we can do if we wanted to, right? Because this is a two-cycle, as we know. Well, being a two-cycle, we can do the LR inverse, I suppose, if we wanted, where you go like this. This will take a two-cycle to a DMP. Well, what's a DMP? That's where in pairs they match in color. In pairs, they match in color. Okay, and that's the kind of conclusion, one of many, that's the kind of conclusion that we would have drawn with using the hidden structures diagram. But you need to realize that before I turned these pairs over, I did not know for sure which were red and which were black. The hidden structures diagram does not give us enough information to know that. Okay? But I do know that these are pairs of the same color. And if that is what you state is the case, then that can be the surprising outcome. Okay? And that surprising outcome is still not too bad. It would carry 3.54 bits. You have to realize 8 cards aren't very many, but it would carry a surprisal punch of 3.54 bits. Well, how would we interpret that? That's like taking 3 or 4, because it's right in between, 3 or 4 fair coins, tossing them up into the air, calling heads, and then have them land heads up. Okay? So quite surprising. Okay? So imagine doing that with 3 or 4 coins. It'll make your friends smile if you successfully predict that. Okay? So anyway, that's just a simple example of the kind of thing the hidden structures diagram will give us. Now, one thing I need to make clear, though, because there's a danger here, as we go up in surprisal values, I don't want to give the impression, because it's not true, that applying group theory is in all ways superior to what we have been learning in the hidden structures diagram, because that is not the case. Because the hidden structures diagram is a whole universe of relationships. Whereas when we go to apply group theory, we have to have a specific group. So think about V8. What are the generators for the Klein 8 group? There's 3 of them, right? You have the pairwise transpose. It's a pretty simple little shuffle. You have the Charlier 1 or 50% cut. Yeah, I mean, the Charlier 1 is is nice. It's pretty convincing. And then you have the packet reversal. Well, packet reversal by itself isn't all that astounding if you were to actually do that. So that's why we kind of recast it in terms of this, the first shall be last and the last shall be first. It gives the spectator the impression that their choices are affecting the outcome, when in fact they're not, okay? So there's a little bit of shenanigans to sell those otherwise very, very simple shuffles, okay? But when you're looking at some of the shuffles that we're doing in the hidden structures diagram, they are far from simple. Far from. Think about the mange. You know, think about the pharaoh. Think about the LR inverse. Think about any of them where we've used the stay stack principle, the Klondike. It just goes on and on. These are complex shuffles, okay? So I just want you to realize that even though we're going to up the surprisal value as we go down this, we're only doing it in a specific case where we're limiting ourselves to just 3 shuffles when we go to apply group theory, okay? So I just want to make sure that we're balancing things. I don't want people to come away with the idea that the hidden structures diagram is just completely inferior to, you know, using orbits or stabilizers or so forth. The problem is your chance or the opportunities to exploit the use of orbits and stabilizers are not as expansive or extensive as your opportunities to use the power of the hidden structures diagram. But if you can use group theory, you can give far more definite and impressive conclusions. You can know far more about the ending structure. Okay, so I will get off my soapbox there. So I just kind of wanted to make sure that people are not coming away with the wrong idea. Okay, so what we're going to do is we're going to go back to an alternating, and I guess we'll just start red, black, just to be the same. Now, I haven't put them in the same order as far as the cards, just the color alternation is the same. Okay, so the orbit. How did we use the orbit of this, viewing this as a CMA sequence now, 1, 0, 1, 0 repeating? How did we use the idea of the orbit? What we discovered was that the Klein 8 group, which is generated by the pairwise transpose and the Charlet 1 or 50% cut, or the packet reversal, that group of 8 permutations preserve each of these structure types. So in particular, if you remember, this CMA structure type here is SOO, right? Because it is a 2-cycle relative to color, same color. It is mirrored relative to opposite color, sorry, stay in the camera, and it is an AMP relative to opposite color, okay? So this is an SOO. So what that means then is we can perform any of those 3 permutations that generate our group in any quantity and in any order, and we will either get back this with red, black, or with black, red repeating. It will be one of those 2. Has to be one of those 2. Now, we won't know how the card, like the red cards, are permuting among themselves, or how the black cards are permuting among themselves. We won't know that, okay? We won't know that ahead of time. You would have to kind of follow what's happening with your shuffle permutations. Okay. So if we go ahead, so for example, so we're starting with red, black repeating. Okay, so we're claiming that you can apply any of the group elements from V8 on this. without, a danger of destroying the CMA structure type. V8 will hold the structure type fixed. Okay, so for instance, we could do a transpose like that. And if you remember, if it's a real transpose, you have to stack from left to right, as you would read a book. That's fine. We can do a Charlier 1, which is just equivalent to a 50% cutting of the cards. We could do another Charlier 1. Well, after what I just explained, we've done nothing with those two together. They've undone each other, but a person watching would not necessarily know that, and almost certainly would not know very readily that that's what has happened. And then we can do a packet reversal. Okay, and we can do the first shall be last. Ask the spectators, tell this one to stop. Stop, stop. Create piles like that, and then true to the name. The first shall be last, the last shall be first, the last shall be first. We stack the last ones all the way to the first ones that were actually dealt out. So that is a first shall be last, last shall be first. It's equivalent to just reversing the cards. And then one thing that we actually pointed out, which is kind of powerful actually, is with the pairwise transpose. I just want to point this out. For it to be a genuine pairwise transpose, we would need to stack left to right, like you read a book. But if we gave them the choice, right? If we gave them the choice to stack the other way, it would actually just be an example of a first shall be last, the last shall be first. It would be a packet reversal, which is one of the generators in our group. So that's perfectly permissible. So at this point, you could actually give them, the option, you want to left to right or right to left. We talked about this more interesting way to do it. And you say, you want clockwise, counterclockwise, clockwise. And so you just go around just like you would in the clock, on the clock, in that direction. Okay. We can perform as many of the transposes, Charlier 1s, or packet reversals as we like, until the spectator feels confident that we really could not know where the cards are, because they're making these important choices. Well, it is true. You don't know where the cards are. The specific cards, you have no idea where they are in here. You can't know unless you are following the shuffles perfectly. Okay, so no one can know that unless you're following those shuffles perfectly. But you do know that it's an alternating packet, either red, black, repeating, or black, red, repeating. Why is that? It's because the CMA sequence, which corresponds to this CMA structure type, is held fixed by the elements in the group V8. Okay? And another way of saying that is the orbit of our 1010, 1010 CMA sequence is the set with itself in it and its inversion. Okay? So we know that this will have to alternate in color. But we do not know if this top card is red or black. We'll need something stronger for that. We just know that it alternates. Well, knowing that it alternates, you can still do something we couldn't do before when we talked about, hey, can we separate the reds from the blacks? No, we can't. Not with the hidden structures diagram. You don't have enough information, right? And let me just show you that it actually is an alternating packet, just so you're clear on that. So we can see here it's alternating. I'm not a bit surprised. In fact, it looks like it's come back to a red on top. It could have been a black. This could have been down there. But we do know it's alternating because this is in the orbit of itself, and then also its inversion. If you had this situation here, would be in that same orbit, right? Okay, so knowing that it's alternating, it tells you quite a bit, because that means if we alternately deal these, I'm just, left, right, I'm just kind of doing it faster, I guess. We know for sure that one of these piles has just red cards and one has just black. But we don't know which is which. The information the orbit provides is not sufficient for us to know that. So we just know that these are the same color, now we know they're red, and that these are the same color. But we could not have anticipated ahead of time which pile was red and which was black, okay? So that's just a simple example of using the power of the information of the orbit to, to have a better idea of the ending structure. And so as mentioned, for backing up here, for the hidden structures, it provided, if you remember, 3.54 bits of surprisal. Now, for using the properties of the orbit, we bump it up a bit. It's 5.12 bits. So, that's getting pretty respectable. That's like taking 5 fair coins, tossing them up into the air, calling heads, and have all of them land heads up. That's the level of surprise associated with our ability to be able to shuffle in the way that we did, as dictated by the spectator as to which shuffle and left, right, and that kind of thing. And then be able to separate the reds from the blacks, okay? So that's the same level of surprise in tossing 5 coins and saying heads on all and have them land heads up. That same level of surprise is what we've just achieved, taking advantage of the orbit. Okay, now the stabilizer, what does that give us that's even more powerful? Well, let's start with, okay, let's just alternate this again, just red, black, and with some ordering of the values. We're not worried about the values right now. Okay, so there we go. So it's the same starting form. Okay, stabilizer subgroup. So we're looking at this CMA sequence, configuration here. And so what is the stabilizer subgroup of that CMA sequence? It came out to be the following subgroup. It has the identity element, which is always a requirement for a subgroup. It has the Charlier with a 50% cut or Charlier 1 shuffle. It has the product, right, the composition of the reversal and the transpose. So you'd have to do both of those. Both of those together put that composition of shuffles in the stabilizer. So it'll leave this exact form alone. And then, or if you do all 3. Okay, so all 3 of them. Okay, so what you could do is, well, there's probably a number of things you could do, I suppose. I mean, you could do what we've done before, where you set up a chart. Yeah, that would work. That would work really well, actually. You set up maybe like 4 rounds, and within each round, the spectator will tell you which shuffle they want first. Like R, T, C, or C, T, R, or whatever. You remember that little table we set up? And what's nice here is you can do as many rounds. You don't have to do 4 rounds. You don't have to do an even number of rounds. You could do 2, or 3, or 5. You can do however many you want. You can let that be completely decided by the spectator. You could keep doing rounds until they kind of get tired and say, okay, well, are you convinced that, really none of us could know where the cards are? And if you do that, and within each of the rounds, you will have done one of these. Now, remember our note down here, the V8 is an abelian group, so this can be rearranged in any order, and it achieves the same outcome. It'll be the same permutation. So you really can permute these. You can, reorder those. So that would work. So just as a reminder, this is the kind of thing I was talking about, where you could go through and do a transpose and then a Charlier 1 reversal for the first round, and then a Charlier 1 here and a reversal, and then a transpose and so forth. So if we went through and did as many, now this time you can do 5 or some odd number of rounds if you want. I suppose you could even just do one more at the end of doing all, number of rounds. You could do one more Charlier 1 by itself. That would be fine. It's in the stabilizer. Or you could do just one more reversal followed by a transposition, or vice versa. That's in the stabilizer, so that won't hurt things. So there's a lot of possibilities here. So why don't we just, let's see, maybe we'll do, sorry about that. Maybe we'll do a transpose. Okay. Now remember, we can't stop there. The transpose by itself is not in the stabilizer, right? This won't be red anymore, the top one. So we could, if we do a reverse, it'll be okay. So you can do the first shall be last, last shall be first. Okay, so if we pair it with that, we're safe, right? Because that would be like doing a reversal, and so now this will be red. And then we can do, all 3 of them if you wanted. Or for that matter, you could just do one more of those. That's red. So anyway, I think and then we do a transpose. And, here, from left to right, for it to be a legitimate transpose. Once again, we can't stop there, right? T's not in here. So maybe we'll just do, we'll do a Charlier 1. Can't stop there either, right? Because that's a CT. I've only done CT so far. So now I have to do a reversal as well. Okay, very good. Reversal. Sorry about that. And now we're fine. It works. So now we get back to an alternating packet with red at the very top. Okay, so because we know that we will preserve the exact form, actually, of the sequence, we can now confidently deal out, sorry about that, everything's askew here. Since we know the exact form of this, namely it's the original form, it's been preserved, we can go left, right, left, right, left, right, left, right. We started with red on top. These are red. Those are black. Red, black, right? So, oops, sorry, went off the screen. Okay, so that's an example of the stabilizer. And then the last one, which actually preserves the entire ordering of the packet perfectly, is where we would have to come up with, and every group will be different. So so every group will be different in terms of what product of elements will be equivalent to the identity, right? So that's very group dependent. So the product of elements, of non-identity elements in a group that end up being equivalent to the identity will completely depend on the group itself, right? So for example, here, what I'm doing is I'm just setting up the same RB repeating packet, right? But the difference is I'm doing it in such a way that we'll know if we preserve the exact order, right? So we have aces, 2s, 3s, 4s. The random ones I was doing before, we'd actually have to write them down on a piece of paper, check at the end if we succeeded, which you could do. This will just make it more transparent, whether we succeeded or not. Okay, so let's think back. V8. So what did we say for V8? Well, golly, if we go back to the Klein 4 group, we know that the product of the transpose, the 50% cut, and the reversal is identity. That wasn't the case for the V8. So what product of group elements would we know is equal to the identity? Well, what we did before was, if you remember, we just took advantage of the information that we had about the order of each of the elements in V8. So each of the generators in V8 has order 2. Okay? So what that means is if we perform each of those shuffles an even number of times, it wouldn't have to be the same even number of times. We could do one for 2 times and one 4 times and the other one 2 times. But as long as you do it an even number of times, the order of those elements will guarantee that that larger product of non-identity elements will actually be equivalent to the identity. Okay? So one way to accomplish that actually is that table again. But this time we would have to be sure that we did everything an even number of times. So here we could actually do the same sort of thing that we were talking about here with 4 rounds. Or you can just do 2 rounds. Because if you go through exactly 4 rounds of this, you will have done each of the shuffles 4 times. Well, the order of each of those group elements is 2. So you will actually get a whole product of things that's equivalent to the identity permutation. We saw that in an earlier, we took advantage of that fact in an earlier class video, I think class video 23. So you could do the same thing there. The thing you wouldn't want to do is you can't do it a 5th time and preserve the exact ordering of this starting sequence. If you do it a 5th time, you will destroy the original ordering. You can't do that. But if each of the permutations that are the generators in the Klein 8 group is applied an even number of times, then you'll end up having a whole product of group elements that are identical to the identity. Okay, so for example, we could do, let's see, we do Charlie A, 1, so we just mentally kind of keep track. So we did a C, we could do a T, left to right, right to left. We could do, well, I guess we can just do an R now, keep track, not get too confused. Okay, this is the reversal. We could say, hey, let's do another, let's do another one of these. First shall be last, last shall be first. That's great. So now we've done C, T, and then 2 R's. We could now do a C if we wanted, a Charlie A. Very good. And then if we do a transpose now, we will have done each of them twice, right? And so just knowing the properties of the group, and in particular the order of the elements that we've just been working with in the group, we will know that this will take us all the way back where you have alternating red-black, and then you'll have aces, 2s, 3s, and 4s. Okay? And then that bumps up the surprisal a lot, right? Up to, whoops, sorry about that, 15.53 bits. So that's like taking 15 coins, tossing them high up into the air, calling heads, and have all 15 coins land heads up. I mean, how mind-blowing would that be to observe in real life, right? Okay, so anyway, I thought we would quickly just show you an example of each of these and how you can see that in this case, taking advantage of group theory, in particular the orbits, the stabilizers, and then the entire group structure in some clever way, we can really generate high values of surprisal.